quick here. So again, as I said yesterday, this is a new unit in Chemistry 30. It's materials science. Just want to go over a few basic things here before we get into it. And as we talked about yesterday, there is evidence that in some bonds, in some compounds, electrons are transferred, and in some bonds, electrons are shared. We're going to talk a lot about that today. Electron affinity is the atom's ability to hold onto electrons, or its attraction to electrons. The word affinity, if you have a particular affinity to something, you have a particular hold on that thing, or a desire to do that thing, or whatever. That's what affinity means. We talked about ionization energy as being the amount of energy to remove an electron. So if you think about the word ion, okay, to make an ion, how much energy is required? So if we have a sodium atom and we want to make an ion out of it, we have to remove one of those electrons. And so there's a certain energy that's involved with that. And of course, sodium, would it be would it be easy to get that electron off, or would it be really hard to get that electron off? What do you think? To form a positive ion? Yeah, easy, because it has one in its outer shell and it's kind of a loner, so it's really easy to get off because it wants to be, sodium kind of wants to be like neon, right? If we had an argon atom, which is a noble gas, and we wanted to take one electron from the argon atom, would that be a high ionization energy or a low ionization energy, do you think? Yeah, it would be high. Why? Because it's got a full octet already. It's happy. It does not want to give up anything. So it would take it could be done, but it would take a lot of energy. It would have a high ionization energy. Okay, electronegativity. We didn't talk about this yesterday, so I want to kind of get into this. If you can write this down just in your notes here, and in the notes you'll see electronegativity is abbreviated here like that. But electronegativity is the relative tendency of an atom to attract electrons to itself when bonded to another atom. So just take a minute to write that sentence down. So if you look at your electronegativity chart, you would see that each element has a specific electronegativity. And I like this chart, actually, because it shows you sort of the higher electronegativities appear to be, in this three-dimensional chart here, appear to be kind of taller, right? It's almost like a bar graph situation. So pretty cool. You can see that the highest electronegativities are in this area right here, right? Fluorine being far and away the highest electronegativity. So what that means is fluorine is a real electron hog, okay? When it gets near any kind of say metal over here like this, it really wants to steal some electrons. Now the metals, right, you got to understand, they're not too interested in keeping their electrons because they have one or two, maybe three extra electrons, and they're just like, yeah, you know what, I wish I could get rid of these so I could be more like the noble gases over here. So fluorine says, hey, let me take yours. So let's see, sodium and fluorine. So on your chart, I'm sorry, it's a little tough to see the photocopy there, but sodium looks like what? 1.01-ish, okay? We have a little discrepancy with this chart on the net here, but we'll use you're going to use yours for your calculations. But sodium here 0.9, okay, or 1.0, kind of is right between your chart and this chart. Not quite as accurate as the one I gave you. But do you see how sodium has less of a desire, so to speak, to hold on to its electron than fluorine? Fluorine really wants to get one more, really, really bad. Okay. Now I'll explain a little bit more why this is, as we kind of move through. But for now, you have to understand that there's there's differing electronegativities here between the elements. Okay. The other term that I want you to know, because we're going to be talking about this, is polarity. Now, when we talk about magnets, when we talk about the Earth and the poles, we're talking about sort of a opposite kind of charge. The poles on the Earth, North Pole, South Pole, the opposite kind of ends of the Earth, right? If you can say ends for semi-spherical shape, but the top, the bottom, the opposite sides. So polarity talks about positive, negative aspects of a structure. So if we just read the notes here, it says, because electrons are not always equally shared in a bond, we just talked about this, right? The affinity and the transferring of electrons in bonds. They're not always equally shared, and so compounds can exhibit polarity, which means that a compound, such as water, let's say water, H2O, just get my pen out here, you have an oxygen, and you have two hydrogens, like this. Water has a more negative sort of end to it, more negative side and a kind of more positive side to it. It exhibits polarity. Why is that? Well, because of the shape of the structure, which we're going to be talking a lot about shapes of different structures coming soon. But because of the shape, it's a bent molecule here, and we have a concentration of electrons sort of on this end over here, and plus the hydrogen lends its electron. It like basically gives its electron up to the oxygen because the oxygen has a higher electronegativity, and so the electrons are kind of more crowded towards sort of this area right here. If this is the entire molecule, right, you see just slightly that the electrons would be kind of on this end of it, right? So you have more of a negative end over here and more of a positive end over here. So that's what polarity is. And most compounds have a slight polarity. The neat thing about the polarity of water molecules is something called hydrogen bonding. And this is why ice is less dense than water, because when these molecules slow down, and what happens is this positive and negative charges sort of start to take over a little bit. And so when water starts to freeze, the water molecules start to slow down in their spinning and in their moving and their motion. And what happens is other water molecules start to line themselves up in a certain way, so that we have so we kind of have, you can see this is kind of positive over here, positive here. So this end is positive, and they start to line each other up. So there's the oxygen and hydrogen, and it starts to kind of do something like this, and you see kind of a predictable geometry here in water, and as it turns to ice. And so ice actually is less dense because those water molecules, they spread out and line themselves up in a certain way. And so in liquid, they're just kind of moving around and they can be closer to one another. But when that motion starts to slow down, they line themselves up. And so that's why ice floats on water. It's less dense than water because of this hydrogen bonding, it's called. The positive end here, the hydrogens, and the negative ends of the oxygens, they sort of line themselves up that way. Okay? So that's that. A little bit on that. Didn't really want to talk about that right now, but there you go. Okay, so on page 303 in your textbook, and again you have this chart, but in the textbook you see a chart as well of the electronegativities there, and I believe that's where I got that handout for you. If you want to just look at page 303 there. And on the diagram that I showed you earlier, that cesium and francium have the lowest electronegativities, and that's in the lower left of the table. Okay, and then the upper right of the table is where the largest electronegativities are, with fluorine having the largest. So let's talk a little bit more about bond types. Okay, now there are intermolecular forces and intramolecular forces. This intra means within, okay? Within the molecule. That's what intra means. Inter, okay, and you've all heard of that. Inter means between different molecules. So intermolecular is how different molecules affect each other. Intra is within. So the bonds or the forces within a molecule. Okay? I'm going to say versus inter. So, yeah, if you want to even jot that down, I guess you could. Forces within the molecule. Within. Okay? And inter is forces between molecules. And Actually, I'd probably expand on that later in the notes, but just because we're talking about it now. Okay, so if we talk about these bond types, and I guess I've kind of put it here inside the compound, right, intra. This means that CS, so cesium and fluorine, are brought near to each other. When they are brought near to each other, the fluorine, because it has a very large electronegativity, will greatly attract cesium's outer electron. It will greatly attract cesium's outer electron. So if we, let's just switch this over here. Okay, so if we look at the notes on one side and we have this diagram over here. So cesium right here, see that? 0.7, cesium and francium, pretty much identical, very low electronegativities. Okay, they want to give up electrons, they don't want electrons. And then fluorine over here, very high. Okay, so when cesium and fluorine are brought near to each other, then what happens is this. I'm going to make this smaller. You guys still see that or not? Sort of. Okay. Lots of desks up in front here. If you can. Anyways, okay, so fluorine will become F minus. Okay, so when they're brought together, now, just atoms floating around, okay? When fluorine sees cesium, it's like, hey, there's an electron I can grab. Because it doesn't care too much about it, and I really, really, really need an electron today. So fluorine grabs that electron as it comes near to cesium, and immediately becomes fluorine negative because it picks up that electron. It kind of gathers that into its outer shell. Cesium at that exact moment will become CS plus 1. Okay? You can make it a little bit bigger for you. So when this happens very quickly, and I'm talking about almost instantaneously afterwards, immediately after this happens, they form a bond. Okay? So because the negative and positive aspects of these ions now take over, and they suck in and become a bond. Within that bond, okay, fluorine still has most of those electrons gathered close to it, and cesium, is just kind of there along for the ride. It's like, well, I'm positive now, and this guy's so negative, we have this attraction, so they form that bond. So the bond actually forms because of the positive-negative charge, and we know that, right? We know that. What you didn't know before, okay, is that the electron gets snatched away by fluorine because there's a high electronegativity, and it's the positive-negative aspect that forms that bond. And that's called an ionic bond. Okay, so yes, a lot of this stuff you should know already, but maybe the reason why, maybe just exactly how this happens, it's described right here, maybe, obviously that you might not have known, Maybe we just think that fluorine minus is just floating around there, it's got this extra electron, and, where does it come from? Well, who knows, it just picked one up from somewhere, but this is sort of a little bit more about, like, how it happens. Okay? Now, we talked about fluorine and cesium where electronegativities are greatly different, right? But what happens when electronegativities are closer to each other? So you've got two elements who have electronegativities that are actually quite close to each other. And if I can, just go back here for a second. Okay, let's put that there. And let's just take a look at this right here. So we're talking about, remember nitrogen and oxygen, right? They can form a compound. What kind of compound is that? Okay, yeah, nitrous oxide or nitrogen dioxide, or yeah. It's not an ionic compound, right? Because we got two nonmetals getting together, and what I've told you before, anything gets together on this side of the table over here, right? Not ionic. It's going to be it's going to be a molecule, not an ionic compound, or it's going to be more of a molecular bond. We have another name for it here now. When electronegativities are closer to each other, one atom doesn't have a much greater attraction for the electrons than the other. And they're both kind of like, hey, I got an electron here, do you want to, you want it? And like, well, the other one says, I don't know, I guess, sort of. Okay, you want to make a bond? Well, okay, I don't know, but I don't know, do you want to take the electron? Well, I kind of do, but not really, I don't want to steal it from you. Whereas fluorine comes in and says, gimme, 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 right? Boom, it's gone. So we're talking about electronegativities, and they're both kind of just pretty chill, and they don't really care. So this is where the electrons are shared in a bond. So remember at the beginning we talked about electrons are transferred or they're shared. And so when electronegativities are closer to each other, then the electrons are shared, and that is called a covalent bond or a molecular bond. And we'll talk maybe a little bit more about the exact difference between those two. But a covalent bond is one where the electronegativities are close to each other. A molecular bond would technically be, I think, when the electronegativities are the exact same. So like if you have H2 or N2, something like that. But anyways, they're used interchangeably a lot. So covalent, here's the new word for you guys, right? Now, we've talked about when they're closer to each other. What do you mean by closer? And this is the big deal here. This is what tells us whether we have an ionic bond or a covalent bond in an atom. When the difference between the electronegativities are less than 1.67. This is sort of the magic number, okay? And that's the difference between the electronegativities. When that difference is less than 1.67, you have a covalent bond. It's a molecule. When the electronegativities are greater than 1.67, which would be the case of fluorine and cesium, we'll take a close look at that in a second, that's when we have an ionic bond. Got it? Yeah, the difference between them. So the difference, you actually take you subtract the electronegativities when you have a difference. So we'll go over an example here in a second. Ionic compounds have electronegativities where the difference is greater than 1.67. And we'll just take a look at an example here of sodium chloride. Now, sodium chloride, before you even look at all this stuff right here, sodium chloride, that's Na plus and Cl minus, right? What kind of compound is that? You know that it's ionic. You know that. Why? Well, why? Because sodium is a metal on the left side of the table, and chlorine is a non-metal on the right side. So remember, up until now, I've said we got an ionic compound if you have a metal with a non-metal, right? Take a look at the charges of the ions. That's how they combine, right? This is what we've talked about. Now, if we go a little bit deeper than that, the reason why this is an ionic compound is because here is chlorine over here, and here is sodium. And look at chlorine's electronegativity. It's up at 3.0. On your chart, in your chart it has 2.83, okay? 2.83. And sodium is, what is that, 1.01? All right, so let's get back to the notes here. Let's just undo that scribble there. Oh, there we go. Here. And so sodium chloride, let's prove that this is an ionic compound. The electronegativity of chlorine minus, so we're talking about a difference, remember, the electronegativity on your chart of sodium. The difference here. Now, yeah, you just use the larger number minus the smaller number. If you go the other way around, it's going to be a negative electronegativity. Just take the absolute value, okay? Just the straight absolute value, the straight difference. Okay, 1.82. So if you have an electronegativity difference that's greater than 1.67, if that difference is greater, then we have an ionic compound. So it's an ionic bond that exists between those. Okay, using the electronegativities on the chart, if we look at CO2, right? CO2, if you look at the difference in electronegativities, we have 3.50 for oxygen here, and 2.50 for carbon. And so the electronegativity is 1.0. That is less than 1.67. Therefore, it's a covalent bond. And we call that a molecule. Not an ionic compound, we call it a molecule. So as an example here, I want you to do this cobalt sulfide, and it's going to be cobalt 2 sulfide, this compound. And so is this ionic or is this covalent bonding? So go ahead and just work that out here and use your chart. What, 1.70, and sulfur is 2.44. Okay, so the difference between those, and again, it doesn't matter which one you type into your calculator first, really, right? If it's a negative, it's just absolute value, so I'll just type in the larger number first. So 2.44 minus 1.7 is 0.74. Is that what you guys got? Okay, so 0.74. So is that greater than 1.67 or less than 1.67? It's less, so technically this would be a covalent bond between the two. Now, you might say, well, Mr. Maxwell here, we've got, the reason why we make this formula is because, cobalt, and you said it was cobalt 2 sulfide. Yes, that's true. So cobalt 2 plus and sulfur 2 minus. This is how they kind of form this compound. You got to remember that the transition metals, they behave quite a bit differently, right? They have multiple oxidation states. This whole d orbital thing really kind of, it makes it a little bit more complicated, right? If we have, these metals over here and the non-metals over here, right, then it's a little bit more straightforward. But what happens when you have cobalt and sulfur? They aren't really that far apart. Plus, cobalt has the highest electronegativity, really one of the highest of all of the transition metals. So it's not wrong to say a 2 plus and a 2 minus, that's what I'm going to form the compound. That's not wrong at all. But just like we have some ambiguity here with the metalloids here, right? Sometimes this is maybe not as it appears. That's why it's important to say, because we would say, oh, ionic compound, right? When we look at the charges, that's how they come together. But now we can be a little bit more exact and say, hey, you know what? This is actually more of a covalent bond. There's not a big difference there. That's okay. I would, at this point in your textbook, turn you to, what is that? Page 305, okay? Page 305 in your textbook. So this is a very similar chart to what's in your textbook. And here's the thing. You see the 1.67 here on this chart? This is electronegativity difference, okay? And this 1.67, this magic number, is the tipping point for bonds that have, that we would call ionic bonds or covalent. Now, notice that at 1.67, the ionic character of the bond, okay, the reason why they get together, that it's because of the differing positive-negative charges, and the whole sharing of electrons. At 1.67, it's 50-50, okay? That's why it's a tipping point. So if we had a difference of 0.65, you see that it's 90% covalent, excuse me, and 10% ionic. And so it's not on or off. It's like, okay, there's a little bit more sharing here than over here. Now this one is hogging the electrons a bit more. So when's the point where we call this an ionic bond, right? And so this is important to note too. So if we got cobalt and sulfur, what did we say? That one was 0.74. So where is that? 0.74 is between here. So we got about 85-15, right? So about 85% covalent, 15% ionic, about there. And here's a little chart here too, I guess, of 0.5. 0.74 is right here. And so notice what they do, and you'll hear this this term as well. Polar covalent, okay? Polar covalent and non-polar. So what they say is they say ionic over here, covalent over here, but there's a huge area where we still have a lot of polarity. Remember we just learned that word today? Polarity. So polar covalent. So that might be a good thing to talk about as well, is polar covalent and non-polar covalent. Non-polar covalent, okay? So if bonds are, if two atoms come together and they have the exact same electronegativities, all right, that means the difference between their electronegativities is 0. Or in that chart that we just saw, when the electronegativities are very low, okay? And I'm going to add to this, or difference in electronegativities is under, and that chart there, let's just go back to that chart real quick. Okay, so we're going to say, what is this? 2, 4, 6, 8. So under 0.4. So under 0.4. It's between 0 and 0.4. Let's just give that for numbers, okay? So is under 0.4. Okay? So between 0, so if we have N2, right? The bond between nitrogen and nitrogen is obviously covalent. It's non-polar covalent. Molecular bond, that's a molecule, and the difference is 0. But it still would be non-polar if it's under 0.4. Let's just say. Polar covalence, okay, so this is between atoms that have differing electronegativities but are still covalently bonded. So let's say instead of electronegativities difference under 1.67, let's say between, hope you haven't got there yet, I'm going to adjust this, between 0.5 and 1.67. And so again, we talked about polarity, and here it comes up again, the polar covalent bond. It's an unequal sharing of electrons, although it's still considered a sharing. And because it's unequally sharing, it makes one end of the molecule partially positive and one end partially negative. And these ends, the positive end, negative end, are called dipoles. Yeah, bring that over here, yeah.